Our team got inspiration from the formation of glaciers. Finding out that the big mountain-like ice could float on the sea, our team wanted to check the theory behind it. Having a little research, we found out that buoyancy depended on the volume of the container. In other words, ships are able to float on water even though they have heavy materials such as huge containers because the power of water upholds the boat against the gravity that tries to make the boat sink. Buoyancy, the ability or tendency to float in water or air or some other fluid, was the main point of our study. Buoyancy can be calculated through the product of the submerged volume of the object, the density of the fluid the object is submerged in, and the force of gravity. Our topic is about buoyancy and density, which are the factors that contribute to the sink and float of matters on water. Our purpose in this experiment is to observe and certificate the force that allows materials to float. We use the formula PVG that is used to calculate buoyancy. PVG can be calculated by multiplying P, the product of the density and the fluid the object is submerged in, V, the submerged volume of the object, and G, the force of gravity. We wanted to check if the density of the fluid, the object, and force of gravity stays constant, the volume of the container would be the primary cause of the container and the coins to sink. Based on this idea, we came up with an hypothesis that under the same volume, the number of coins each container could uphold would be the same no matter what kind of material for the container is used. To replace the loads in the ship, we use 101 coins and use 3 kinds of containers: paper cup, aluminum foil cup, and a plastic cup. Also, we measure to the nearest integer or to the nearest tenth for every data set in the experiment.
Now that we have set our topic, purpose, and hypothesis, we will go through our experiment. For the experiment, we need to prepare a knife, a ruler, a water tank, coins, and 3 different material cups, which are plastic cup, paper cup, and aluminium cup. In order to make sure the independent variable we want to check is the use of different material, we would calculate the volume to be the same for each type of container. So the next step would be measuring the radius and the height of each container. For paper, it has a radius of 2.5 cm, height of 7 cm, and a volume of 155.7 milliliter. For plastic, we have a radius of 3 cm, height of 5.5 cm, and a volume of 155.5 milliliter. And finally, for aluminium, we have a radius of 2.5 cm, height of 7 cm, and a volume of 155.7 milliliter. We can know that 3 containers have similar volume, and this is really needed since our buoyancy would depend on the volume of the containers. After we measure the radius and the height of each container, we are going to fill the water tank with water. And we are going to put one of our containers, and then one by one we are going to stack the coins into each container and check how many coins could the container uphold. We're going to repeat the trial 10 times since we need to get a correct mean number. Having an experiment only once could lead to a biased mean number of coins that containers could uphold, so repetition is necessary. And finally, we are going to record the result. After the experiment, we knew that every container approximately had a constant mean number of coins each could uphold. Not even conducting a hypothesis test, we could know that there is a definite difference among the 3 different containers. Such result contradicts our initial hypothesis. Why would each container have a different result although they all have the same volume? It is because of the density of our containers. Although the same volume, different mass causes different density that would eventually lead a heavier container to sink easily. Based on the re-examination, we came up with the second hypothesis, which is, considering both buoyancy and density, under the same volume of containers, the heavier container would sink easily than the lighter containers. That is, aluminium, which is the lightest out of 3, would uphold the most coin. Also, during the conduction of our experiment, we found out crucial mathematical errors that influenced the results. Additionally, we found out the water influx through the crevice between the aluminium. And finally, we figured out paper container gradually gained weight as it absorbed water. To overcome such problems, we double-checked our mathematical calculation, replaced paper cups every 3 trials, and made sure no crevice exists for the aluminum container. So we conducted our second experiment. In order to know the density, we first had to measure the weight of each containers. Therefore, we needed a scale to measure the weight. Aluminium was the lightest, paper the second, and lastly, the plastic. Once again, we filled the tank with water, set one of the containers, and stacked the coins. For every container, the experiment was repeated 10 times, just like the first experiment. Then we recorded the results. Now all the result was recorded, and as we expected, aluminium held the most coin and the plastic held the least coin. From this experiment, we were able to know that although the same volume, the number of coins the container could uphold is different depending on the mass of the container. Based on our study, we were able to have a deeper understanding of the factors that allow ships, glaciers, and even humans to float on water.